There are 118 known elements in the universe. Everything you have ever touched, eaten, breathed, or loved is made from combinations of these 118 building blocks. For most of human history, we had no idea they existed. And when we finally found them, we had no idea how to make sense of them. This is the story of the map that changed everything. By the 1860s, chemists had discovered more than 60 elements. And they were drowning in them. Each element seemed to behave differently. There was no obvious pattern, no logic, no order. Scientists were cataloging substances they could not explain, in a language they had not yet invented. The universe had given them the pieces. But no one could see the picture. In 1869, a Russian chemist named Dmitri Mendeleev sat down to write a chemistry textbook. He needed to organize the elements for his students. So he wrote each element on a separate card. Mass, properties, behavior, then he arranged them in order of atomic weight. Something extraordinary happened. When he lined them up, patterns emerged. Elements with similar properties appeared at regular intervals. He built a table, and wherever the pattern demanded an element that had not yet been discovered, he left blank spaces. He predicted those missing elements would be found. He described their properties in advance. Within 15 years, 3 of them were discovered. Each one matched his predictions almost exactly. The periodic table was not just a list. It was a prophecy. Mendeleev ordered elements by atomic weight. But there were problems. A few elements seemed to be in the wrong place. In 1913, a young physicist named Henry Moseley solved the mystery. The real organizing principle was not weight. It was atomic number, the number of protons in the nucleus. Every element has a unique atomic number. Hydrogen has 1, carbon has 6, gold has 79. When Moseley reordered the table by atomic number, every anomaly disappeared. Every element fell into its correct position. Atomic number is the element's true identity. Everything else follows from it. The periodic table has 2 axes, and both of them matter. The horizontal rows are called periods. Each new period begins when a new electron shell opens up around the nucleus. The vertical columns are called groups. Elements in the same group share the same number of outer electrons. And that makes them behave almost identically. Group 1, highly reactive metals. Group 17, highly reactive non-metals. Same column, same personality. Group 18 is different from all the others. These are the noble gases. Helium, neon, argon, krypton, xenon, radon. They do not react with anything. They do not bond. They do not combine. Their outermost electron shells are perfectly full. They have everything they need. They want nothing. For a long time we called them inert gases. Then we called them noble. Because they stand apart, aloof, untouchable, like royalty. The periodic table encodes trends. Patterns that repeat. Properties you can read off the table like a map. Atomic radius. As you move left across a period, atoms get larger. As you move down a group, they also get larger. Electronegativity. The pull an atom has on electrons. It increases as you move right and upward. Fluorine, in the top right corner, is the most electronegative element in existence. Ionization energy. How much force it takes to remove an electron. It rises across periods and falls down groups. These are not coincidences. They are consequences of electron structure. The table makes them visible. Everything about the periodic table comes down to electrons. Each atom has a nucleus of protons and neutrons at its center. Around that nucleus, electrons occupy regions of space called shells. The first shell holds 2 electrons. The second holds 8. The third holds 18. When a shell is full, the next electron must start a new one. That is what creates a new period in the table. But electrons do not just sit in shells. Within each shell they occupy sublevels called orbitals. Each orbital holds 2 electrons. And the shape of those orbitals determines how atoms bond with one another. This is why carbon forms 4 bonds and forms the backbone of all life. This is why oxygen is reactive and gold is stable. Electron configuration is the grammar of chemistry. In the middle of the periodic table sits a wide block of metals. These are the transition metals: iron, copper, silver, gold, platinum, titanium, chromium. They are different from the metals on the left. Their outer electrons are not in the outermost shell. They are filling inner d orbitals. This gives them unusual properties: multiple oxidation states, rich colors, catalytic power. Iron makes your blood red. Copper makes your veins look blue through your skin. Chromium makes steel stainless. The transition metals are the workhorses of chemistry and the foundation of modern industry. Below the main table sit two long rows of elements that most people have never heard of: the lanthanides and the actinides. They are separated from the main table to save space. But they are real, and they matter. The lanthanides include the rare earth elements: neodymium in your phone speaker, cerium in catalytic converters. They are not actually rare, but they are hard to separate. The actinides are heavier and stranger: uranium, thorium, plutonium. All of them are radioactive. Their nuclei are unstable. They decay, they split, they release energy measured in megatons. The actinides are the elements that tortoise the power inside the atom. Today the periodic table has 118 confirmed elements. The first 94 occur naturally on Earth. The rest have been created in laboratories, one atom at a time, in particle accelerators around the world. They exist for fractions of a second before decaying. But they exist. Element 118 is called organessen. It was first synthesized in 2002 in Russia. It has a half-life of 0.89 milliseconds. Long enough to confirm, long enough to name. The greatest power of the periodic table is not description. It is prediction. When Mendeleev left gaps, he did not just say elements were missing. He described them. Eka-aluminium, he called one. It would have an atomic weight of 68. A melting point below 30 degrees Celsius. It would dissolve in acid. In 1875, French chemist Paul-Émile Lecoq de Boisbaudran discovered gallium. Atomic weight, 69.7. Melting point, 29.8 degrees. It dissolves in acid. Mendeleev had described an element that did not yet exist. That is not chemistry. That is prophecy backed by mathematics. Where do elements come from? The answer is one of the most beautiful in all of science. Hydrogen and helium were created in the first 3 minutes after the Big Bang. Everything else was forged inside stars. Nuclear fusion in stellar cores builds elements up to iron, fusing hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. But iron is the end of the line. Fusing iron absorbs energy rather than releasing it. When a star's core turns to iron, it collapses. In less than a second, the outer layers rebound and explode. A supernova. In that explosion, for a fraction of a second, conditions exist to create elements heavier than iron. Gold, platinum, uranium, iodine. Every element heavier than iron in your body, in your ring, in your phone, was forged in a dying star. You are made of stardust. That is not a metaphor. It is nuclear physics. Consider table salt. Sodium is a soft, silvery metal. Drop it in water and it reacts violently, skittering across the surface and igniting. Chlorine is a toxic yellow-green gas. Breathing it in concentration can kill. Combine them, one sodium atom, one chlorine atom. The sodium gives up one electron. The chlorine takes it. Both become stable. Both become calm. And what you get is sodium chloride. Salt, the thing you sprinkle on your food. Two deadly substances. One completely safe compound. This is what the periodic table predicts. Sodium in group 1 wants to lose one electron. Chlorine in group 17 wants to gain one. They are made for each other. The periodic table is not just a scientific document. It is the blueprint for modern civilization. Lithium in your phone battery. Silicon in your processor. Tungsten in your light bulb filament. Platinum in your catalytic converter. Titanium in your aircraft frame. Indium and tin in your touchscreen. Gadolinium in MRI contrast agents. Technetium in medical imaging. Bismuth in stomach medicine. Germanium in fiber optic cables. Gallium in LEDs. Every technology that defines modern life draws from the periodic table. When a new material is needed, chemists do not guess. They look at the table. They find the element with the properties they need. And they go to work. The periodic table is also a human story. Ancient alchemists hunting for gold. Lavoisier defining elements for the first time. Marie Curie isolating radium in a leaking shed, not knowing it would kill her. Glenn Seaborg discovering 10 elements and having one named after him while he was still alive. Thousands of scientists across centuries, each one adding a piece. The table carries all of them. The periodic table can be divided into 4 blocks, each defined by the type of orbital being filled. The S block, groups 1 and 2 on the left. Hydrogen and helium, these elements fill S orbitals. Highly reactive, low ionization energy. The P block, the right-hand section, groups 13 through 18. These elements fill P orbitals. They include metals, metalloids, non-metals, and noble gases. The D block, the transition metals in the center, filling D orbitals. Complex chemistry, multiple oxidation states. The F block, the 2 bottom rows, filling F orbitals. The lanthanides and actinides. 4 blocks. 1 table, a complete map of electron behavior. You use the periodic table every day without knowing it. The iron in your blood carries oxygen to your cells. The calcium in your bones gives them strength. The potassium in your banana keeps your heart beating in rhythm. The oxygen you breathe right now. The carbon in every molecule of every food you eat. The periodic table is not something that exists in a textbook. It is what you are made of. Element 118 is not the end. Physicists predict that around element 120 to 126, there may be an island of stability. A region where super-heavy elements decay more slowly. Perhaps stable enough to study. Perhaps stable enough to have properties we have never seen. Island of stability. It sounds like science fiction. But so did Aganesson, until 2002. The table is still being written. The periodic table is a map of everything that exists. Every atom in your body. Every star in the sky. Every material we have ever built with. 118 elements. Infinite combinations. And the map is still growing. Subscribe to Knowable. New science explained as every week. See you next time.